Hello mortals, welcome to your one-stop shop for all news science. In this video, we will look over some of the newest developments and discoveries across various scientific disciplines. Buckle up folks, we begin now. For our first story, we have some eggheads who finally figured out how to beam solar energy from space directly to Earth. There's a recent concept known as Cassiopeia, which comprises two 2-kilometer wide reflectors that can be directed. These reflectors are used to redirect sunlight onto an array of solar panels. The solar panels then power transmitters, about 1,700 meters in diameter, which can be aimed at the ground station. The projected mass of this satellite is around 2,000 tons. Contrasting Cassiopeia, there's another design called SPS Alpha. In this architecture, the solar collector takes on a different form. It's a sizable structure composed of numerous small, modular reflectors referred to as heliostats. What sets them apart is that each heliostat can move independently. These heliostats are produced in large quantities to lower production costs. In 2023, researchers at Caltech initiated the Maple project, a small-scale satellite experiment aimed at beaming a small amount of power back to Caltech itself. The success of Maple demonstrated the feasibility of using this technology to transmit power to Earth. The potential of space-based solar power, SBSP, is immense, especially in assisting the UK's target of achieving net zero emissions by 2050. Surprisingly, the current government strategy doesn't include SBSP as part of the solution. An independent study revealed that SBSP could contribute up to 10 gigawatts of electricity by 2050, a significant quarter of the UK's existing energy demand. This form of power delivery offers reliability and stability to the energy supply. The economic impact is also noteworthy, as SBSP could generate a multi-billion-pound industry, generating around 143,000 jobs across the nation. Evaluating SBSP's feasibility, the European Space Agency is actively assessing the technology through its Solaris initiative, and this might lead to a comprehensive development plan by 2025. On a global scale, several countries have announced their intentions to transmit power to Earth by 2025, with the plan to scale up these systems in the subsequent decades. Given that the technology seems promising, one might wonder why SBSP isn't already in use. The primary limitation revolves around the substantial mass that needs to be launched into space, coupled with the associated cost per kilogram. Enterprises like SpaceX and Blue Origin are working on heavy-lift launch vehicles, focusing on reusability to drastically reduce the venture's expenses by as much as 90%. Even with the capabilities of SpaceX's Starship vehicle, which can transport a whopping 150 tons of cargo to low Earth orbit, the SBSP satellite would still necessitate hundreds of launches. Some innovative approaches, such as 3D printing certain components like long structural trusses in space, could address these challenges. Now that we are on the topic of energy, our next story features some absolute chads who decided to turn concrete into a battery. Scientists are in a perpetual quest to enhance renewable energy storage, and now, MIT researchers have uncovered a method to transform cement in an ancient substance into a colossal supercapacitor. This electrified cement holds the potential to convert building foundations and roadways into virtually boundless batteries. The concoction of this new material involves a collaboration between experts from the Massachusetts Institute of Technology, MIT, and Harvard University. They combine cement, water, and carbon black, a material akin to finely powdered charcoal produced from incomplete combustion processes. Admir Mosik, a materials scientist at MIT, describes the material's intrigue. You have the most widely used human-made material, cement, paired with carbon black, a historically significant material. The Dead Sea Scrolls were written with it. When you combine these two millennia-old materials in a specific manner, you generate a conductive nanocomposite. And that's when things get really captivating. Within the reacting cement, the carbon black particles tend to cluster in voids formed as water is absorbed, giving rise to wire-like formations in the cement. This augmentation in conductivity bestows upon the modified cement the capacity to function as a supercapacitor, a power source akin to a battery, but with the ability to swiftly store and discharge electrical energy. By introducing a conventional electrolyte material like potassium chloride, the charged particles disperse within the material, facilitating energy storage and release by the supercapacitor. At present, these cement-based capacitors are relatively modest in size, capable of illuminating a handful of LED light bulbs. However, the materials utilized are economical and abundant, and the scaling process holds promise. The team's next endeavor involves crafting a device similar in size to an automobile battery. Envision a house founded on supercapacitor cement. It could potentially amass enough energy to power the entire house for a day, as the researchers propose. This energy could be harnessed from renewable sources such as solar or wind. Additionally, this composite could be employed on roads to supply energy to electric vehicles as they traverse, an innovation being explored by various research projects. A balance exists between storage capacity and structural integrity, but the cement's adaptability caters to diverse usage scenarios depending on the requirement. In their published paper, the researchers articulate, these properties point to the opportunity for employing these structural concrete-like supercapacitors for bulk energy storage in both residential and industrial applications, ranging from energy autarkic shelters and self-charging roads for electric vehicles, to intermittent energy storage for wind turbines. That's pretty cool and all, but check out our next story where another bunch of gigachads made an actual working weight loss drug. Mice subjected to a diet high in sugar and fat throughout their lives managed to evade weight gain and safeguard their liver health when treated with an innovative experimental drug. The novel small molecule drug, known by the acronym CPACC, was formulated by a team led by the University of Texas Health Science Center at San Antonio, UT Health San Antonio. This drug acts by restricting the influx of magnesium into the mitochondria, the cellular components responsible for energy generation and calorie burning. Mitochondrial irregularities have been implicated in various conditions, including obesity, diabetes, and cardiovascular diseases. These findings stem from years of dedicated research, explains Madesh Muniswamy, a molecular biochemist at UT Health San Antonio, and the senior author of the published study. In addition to calcium, potassium, and sodium, magnesium stands as one of the 4 major positively charged ions integral to numerous bodily functions. Magnesium plays diverse roles in maintaining well-being, such as regulating blood sugar, blood pressure, and aiding in the formation of robust bones. However, excessive magnesium hampers energy production within mitochondria. It acts as a brake, causing a slowdown, elucidates biologist Travis Mataris from UT Health San Antonio, co-lead author of the research. The discovery of this new drug emerged during an exploration of the consequences of eliminating a specific gene called MRS2. This gene encodes a magnesium transporter protein known as Mrs2, which functions as a channel for magnesium movement across the mitochondrial membrane. The study scrutinized the impact of a prolonged diet rich in fats, sugars, and calories, comparing normal mice with those having their Mrs2 gene deleted. Deletion of MRS2 led to leaner, healthier mice with enhanced sugar and fat metabolism within their mitochondria, even when consuming a Western diet starting at 14 weeks of age and continuing for up to a year, a considerable duration in a mouse's lifespan. In the orchestration of sugar and fat metabolism in response to eating and fasting, the liver holds a pivotal role. While resilient, the liver has its limits. Significantly, the mice with Mrs2 deletion displayed no indications of fatty liver disease in their liver or fat tissues, a condition often stemming from an imbalanced diet, obesity, or type 2 diabetes. Mitigating the adverse effects of prolonged dietary stress was achieved by lowering mitochondrial magnesium, explains biologist and co-lead author Manigandan Venkatasan from UT Health San Antonio. Subsequent experiments administering CPACC yielded similar effects to MRS2 gene deletion. The drug achieves this by inhibiting the magnesium channels encoded by the gene, resulting in lean and healthy mice due to the reduced transport of magnesium into the mitochondria. While the findings hold promise, it's important to note that outcomes observed in mice might not directly translate to humans. The study acknowledges its limitations, particularly the use of long-term dietary stress to mimic metabolic syndrome in humans. Exploring the effects of short-term dietary stress could offer deeper insights into MRS2 deletion's primary effects. Additionally, the comprehensive deletion of the Mrs2 gene makes it challenging to discern how individual tissues impact metabolic regulation. Given the widespread expression of MRS2, the researchers stress the necessity for further investigations into its effects on various organs, such as the brain, heart, kidneys, lungs, and skeletal muscles. A patent application for CPACC has been submitted by the researchers. Madesh Muniswamy remarks, "A drug that can reduce the risk of cardiometabolic diseases, such as heart attack and stroke, and also reduce the incidence of liver cancer, which can follow fatty liver disease, will make a huge impact. We will continue its development." For our last story, we have some beautiful new images of a dying star. The intricate luminous remnants enveloping a fading star have been unveiled in a remarkably detailed manner through images captured by the James Webb Space Telescope. Fresh observations of Messier 57, also known as the Ring Nebula, were introduced earlier this month. Now, after careful refining and meticulous processing, the images provide an unprecedented view of the dying star. Leveraging the near-infrared capability of NIRCam and the mid-infrared capacity of MIRI, the observations offer distinct insights into the final stages of a sun-like star at the core of the nebula. NIRCam's observations bring to light the intricacies of the filaments and knots within the nebula's inner regions, whereas MIRI unveils the delicate patterns of concentric features in the outer segments. The Ring Nebula, located approximately 2,750 light-years away, falls under the category of a planetary nebula. This term denotes the concluding phase of a star which, in its earlier stages, resembled our own Sun. As Sun-like stars gradually exhaust their hydrogen fuel, essential for core fusion, they undergo destabilization, leading to the expulsion of their outer layers. The core of the star, no longer upheld by the outward pressure generated from fusion, succumbs to gravitational forces, ultimately collapsing into a white dwarf. And that's the video. Join us next week, as I will cover some more news about science in a similar manner. Consider liking and subscribing. If you do, I will love you forever. Until next time, mortals.